Thank you, Martina, and thank you to the organizers for inviting me. I'm very happy to be here. It's so fun to see everybody, and there's so much to discuss. I only have 30 minutes, so I'm going to have to go a little fast. But as you all know, we have just passed the 10th anniversary of gravitational waves. We have now 150 or so official public events, but 200 or so more. And so if you study binary neutron stars, times are maybe a little bit sad, but if you study binary black hole populations, it's actually a great time to be alive. That is in particular because with so many events, we now have enough systems to start to be able to not just look at the full population, but dissect and cut inside this population of binary black holes and ask questions about subpopulations within these black holes. So the big question for all of these binary black hole systems remains, how did they form? As you also probably know, we have many proposed formation channels, and we typically still divide them or subdivide them between roughly isolated channels and dynamical formation channels because they make some very distinct predictions for what the final masses and spins, etc., would look like. Now, over the past years, or maybe 5 years ago or so, I would say that many of us would have the one channel to rule them all mentality, which was very much based on a merger rate, saying that my formation channel can form all the merger rates that we see today. But even then, it already became quite clear that maybe one channel is not sufficient to explain the whole distribution, and we kind of even tilted the other way around to go to one formation channel for every system, which I think is also not optimal. Probably the reality is somewhere in between, but all is not lost because we can actually make progress if we don't just look at the merger rates, but for example, we look at the mass function, which is already one dimension extra, and the gravitational wave, as Aditya showed us this morning, gravitational waves very clearly for the binary black holes show structure in the mass function. Some of these features are more or less certain, but I think nobody can deny that that there is structure right now. But as I mentioned, we can go one step further now with hundreds of detections, and we can ask for each of these kind of subsections of, for example, the mass function or subsections of the binary black hole population, are there other properties that they share in common? And do these properties reflect their formation history? So many people have started to do this, especially in the last months or so. And I want to highlight this particular paper from, for example, this paper by Sharma Banerjee, where they fit multiple mass thresholds and try to find if there are common mass ratios or spin populations for systems at lower or higher masses. They claim that they already see some evidence for 3 distinct subpopulations at low masses with small spins and small q, or flats in q, at the 30 solar masses area with equal masses, and above with lower mass ratios and flat spins, or broader spins. Now, what does this mean? Do these subpopulations truly show us something about the progenitor formation? Well, I'm going to address this question throughout the rest of this talk, starting at the low masses and moving to increasingly high masses, and I hope I make it all the way to the end. But I'm going to start with the simplest, kind of simplest theory. I'm not trying to offend anyone here, but maybe the features that we see in the mass distribution are directly a consequence of the way that stars end their lives. So there's these papers from Fabian Schneider and collaborators that say there's compactness peaks, and these compactness peaks, in long story short, lead to predictions for which stars explode and which stars don't. And because they're very related to the masses of the stars or the cores at the end, they also lead to very specific predictions for the mass distribution. And in particular, Reinhold Wilcox, in a very recent study, implemented kind of a mass function, a random mass function based on this model into Compass, and found that regardless of a lot of the uncertainties in binary physics, you will keep a trimodal binary black hole population. I wouldn't say it's a perfect fit, but they definitely say there are multiple peaks and you cannot get around. So maybe it's all core collapse supernova. I'm not going to talk too long about that because the next talk is Adam, and I think he has much more interesting things to say about that than I do. So I'm going to go here and argue that even with a very dumb core collapse supernova model or a very simplified model where you just say more massive cores lead to more massive black holes, we still expect structure in both the mass function, spins, etc., based purely on the binary evolution or the formation channel, or in other words, the pairing function, if you come from the gravitational wave inference. And so my favorite theory is that maybe the systems at the low mass end of the black hole spectrum come from stable mass transfer. The stable mass transfer channel in isolated binaries is where you have just isolated binaries, no dynamical effects, that only experience stable mass transfer. And because there's strong constraints on what stable mass transfer is, this leads to specific final masses. And in particular, we showed in a paper from 2022 that this could lead to a peak at 9 solar masses. But there's more. So this is basically kind of showing that cartoon picture of the stable mass transfer channel. And the main physics that you have to keep in mind is that there is some dependence of mass transfer stability on the mass ratio of the systems that are involved. And so this is what places this limit on the masses that are outcoming and the mass ratios that are outcoming from this. But see also, I think Jacob Klenke has a really interesting paper on maybe its orbits more than mass ratios. But I trust this in the qualitative sense. But I said there's more. So basically, this doesn't just lead to a peak at 9 solar masses, but this restriction leads both to a restriction of the masses that come from the initially more massive star and the masses of the black holes that come from the initially less massive star. So the more massive star is this black line, and the black holes that come from the initially less massive star is this red line and the orange population. And now Gina Chen, a PhD student with Kitty Breivik at CMU, has been investigating this model and saying, what does that mean for the mass function of the stable mass transfer channel? And we're finding that the stable mass transfer channel predicts 2 peaks in the mass function. One peak at 9 solar mass or 10 solar masses that comes from the initially more massive star, and a second peak where the mass ratio is reversed. So it comes from the more massive black hole comes from the initially less massive star. Now I've been telling, don't just look at the mass, look at the other properties. So she did that as well, and this has a very strong prediction also for the mass ratio distribution that you should get. The mass ratio reverse systems basically flip over and are close to 1, but still peaking away from equal masses. And the non-mass ratio reversed have a much flatter, broader, low mass ratio distribution. You can look at the same population or the same plot in the primary secondary space. And then you get kind of 2 distributions. This peak at around 10-ish solar masses, that is a little bit more away from equal masses. And the blue population is the mass ratio reverse systems that lie closer to the equal masses. Where exactly these peaks lie, of course, depends strongly on your assumptions of mass transfer stability, mass transfer accretion efficiency, etc. But the fun thing is we understand how to influence them, and we understand qualitatively why these peaks should or should not be there. If by eye you compare this to the O4 data, yeah, I think you can squeeze your eyes and say like, oh, it looks kind of maybe not completely different. But we can do better than looking by eye and squeezing our eyes. And so that's what Jackson is actually doing. So Jackson Godfrey is a PhD student with Ben Farr. She just graduated, and basically she took this very strongly parametrized model for the mass ratios and turned it in this model. So what you're seeing here is the orange is the mass ratio that is truly the black hole that came from the originally less massive star over the black hole that came from the originally more massive star. And the blue line is what you would observe. So the blue line is the less massive over the more massive black hole as we see it. Because of course, when we see it, we don't know if it came from the originally less or more massive black hole. But what I want to point your attention to is that you get this interesting double structure again, as Gina was also finding, with this flat lower part of non-mass ratio reverse things and this kind of higher equal mass ratio at the other side. Now, these are preliminary results, but Jackson is basically taking this model for the mass ratios and the 9 solar mass peak as observed in gravitational waves, and she's asking what kind of mass ratio, if I take this strong mass ratio model, fits to the data. And she finds that in 40% of the cases, the data for the 9 solar mass peak indeed prefers a mass ratio distribution that peaks away from 1, and that is not requiring that any of the systems in there have to be mass ratio reversed. In 60% of the cases, she does still require mass ratio reversal, but the fraction of the systems in that peak that contribute to that 9 solar mass peak that are mass ratio reversed is always low. It's somewhere at around 30%. So again, this is preliminary work, but the next step will be to look at the 20 solar mass peak as well and see if we can infer a higher fraction of mass ratio reverse there. If we can see this behavior of a lower mass ratio and a higher mass ratio peak, both away from completely equal. Okay, so that is all for kind of theory 2 for the stable mass transfer channel. But now so much is happening, and as we also saw this morning, there have been 2 systems already released from the next catalog, so not from Gravitational Wave Catalog 4, but from the 05, I guess, or 04B. And these systems are very interesting because they both have a very well-measured spin that is away from being 0, and the systems are furthermore misaligned. One of with the orbit, the blue one, is positively aligned, so it has a positive chi effective. And the green one, I'm not going to say the telephone number, it's too much, is anti-aligned, most confidently. And what's more, these 2 systems have mass ratios that are not 1. So they're confidently low mass ratio systems. And lastly, they are also systems that are of about 15 to 20 solar masses in primary mass. And so when people saw this, they immediately thought, maybe these are hierarchical mergers. That can very well be, because again, for hierarchical mergers, we expect unequal mass ratios, a broad distribution in the spins, and misalignment. You can go even as far as taking this already into a population model, which is what Hui Tang did in this paper, where they made some pretty strong assumptions, saying that the mass function has to follow this particular sequence of spin distributions. So basically they say at low masses there has to be a narrow low spin effective. In between there has to be a narrow plus broad, then it has to be narrow again, and then it can be narrow plus broad. If you do all that, then you infer that there might be evidence for a high fraction of narrow plus broad, I'm going to call it narrow plus broad, at around 15 solar masses, and a high fraction for the narrow plus broad at the high masses. They interpret this as the secondary peak, or the systems at 15 solar masses come from hierarchical mergers. I want to warn a little bit that you get what you order if you do inference, and so if you order if you have a very strong order on your gravitational wave data, you will find something there. I'm not going to say it's not hierarchical systems. There's also much more knowledgeable people in the audience here. I think Salva's also giving a really interesting talk later this afternoon on gravitational wave inference. But so I would say it's tentative, but I just want to give the full spectrum of ideas that are out there. Okay, am I doing time? Halfway. So far, I've just been focusing on the lower mass end, but I promised I was going to move up in masses a bit. And I think as you go higher and higher in mass, it's more and more likely that more parts of the gravitational wave population are dominated by dynamical formation or hierarchical, even hierarchical mergers. On the flip side, I'm also very convinced that the 9 solar masses and the binary neutron stars are all isolated binaries. But I was promising to go up to the higher masses, so let's do that. And let's talk about this peak at about 35-ish solar masses. In maybe more than 5 years or so ago, people were very convinced or suspected that this peak was caused by parapulsational instability supernova. However, I think more and more people now don't believe this. It seems to be mostly just at the wrong location. The biggest argument behind this is the carbon-oxygen rate that you need to get the peak to occur at 35 solar masses just does not match up with laboratory experiments. I'm not going to go too deep into it, but I have backup slides if people are interested. But that kind of leaves this 35 solar mass feature unexplained. Why is there an added number of systems there? Why is there a feature in the black hole mass function? Well, this is a question that Shmendra took up. Shmendra Roy is a final year PhD student. He's working with Will Farr, and he's been working a lot with me. And he did this really cool paper where he basically cut out all the systems that can realistically contribute to the 35 solar mass peak to investigate their properties alone. Now, for the inference aficionados among you, this is kind of a complementary way of doing it as opposed to, for example, taking a spline or garbage collector function, or just trying to fit everything with a very flexible model. And the benefit here is that if you do this cutout, you're not so much skewed by what happens at other parts in the distribution. So really, it's a complementary method. And so he looked at what are the other properties of systems in here. I'm going to go over them quickly. Firstly, he confirmed there is a feature at 34 solar masses. So that's great, consistent with other predictions. He also found that indeed the mass ratio of these systems are preferring equal masses. This is again confirmed later on also by the LVK paper and Banagiri's paper. The spins are low but positive, and the redshift evolution the rate is rising with redshift. Both of these are consistent with what LIGO has inferred for the global population as well. Okay, great, but what does this mean? So to answer that question, we don't just want to infer what the properties are, but we want to compare them also to the predictions from different formation channels. And so that's what we're doing here. Many different formation channels have been proposed to cause a peak at 35 solar masses. And what I mainly want you to take away from this plot is that we've all been focusing very much on trying to get a peak in the masses, and we've been focusing much less in trying to also match the predictions for the mass ratio and the spins, of course. And so now that we have this power, now that we have this knowledge, we should go ahead and take our models and make predictions also for these other properties of systems in a 35 solar mass peak. So we've done our utmost best to take both these quantitative and qualitative predictions from models that exist in the literature and convert them into check marks, crosses, or kind of question marks. Black crosses are, if it's black, we don't really know for sure. If you see anything you vastly disagree, please let me know. We're happy to, update this. But what is important to note is, again, that there's many models that are missing, or many predictions that are missing. And so it's hard to confidently, completely exclude formation channels from forming this peak. But I do also want to highlight that none of these channels give you beautiful green check marks everywhere. And so this is why we call it the mid-30s crisis of binary black holes. They just don't know what to do. But, well, I do know what we should do, and that is look more in detail at each of these different models and see if we can make predictions for these other properties. And so here I want to highlight work by Lucas de Sa, who is now a postdoc in Heidelberg, and he's investigating in particular the model for chemically homogeneous evolution and seeing if that could explain this peak. So chemically homogeneous evolution is where you have two stars in a very tight orbit, so closely locked together, they're tidally locked, they rotate so fast that they get into sweet circulations, mixing the stars throughout. To get this kind of evolution happening, this leads to very different evolution in stars than the normal core envelope evolution. But to be able to get this evolution, there is a very narrow common envelope, chemically homogeneously evolving window. And so this window in Zam's masses and periods is bounded at the bottom by not creating stellar mergers, if you put them too close. It's bounded on the left by the masses, because this mixing is only efficient for massive enough stars that are, for a large part, radiatively supported. And it's bounded at the top by the periods to merge within a Hubble time, because if you put them much too far away, they're not going to interact, they're not going to be chemically homogeneous. But furthermore, the winds play an important role at those wide separations, because these stars might look like helium-enriched or Wolf-Rayet-like stars that might experience strong winds that can drive them further apart and prevent a merger. So what Lucas has been doing is running a whole big grid of these chemically homogeneous models and trying to do population synthesis with these MESA models to infer basically what are the final black hole masses that we get and how often would they merge. And this is kind of the merger rate with redshift that we get, which surprisingly actually does lead to somewhat of a peak at about 30 solar masses, but it doesn't give you this sharp decay towards higher masses. And there's also some interesting stuff going on with redshift evolution. I do want to say one asterisk that their parent stability is not taken into account here. So a big chunk of these systems would just explode from parent stability. But there's another big question, and that is, what about the spins? And so if you assume, the bottom line is, it's all about the angular momentum transport that you assume. If you assume Taylor-Sprout angular momentum transport, then all of these stars will be rotating way too fast, and you get really high spins, which is inconsistent with the gravitational wave data. If you take the Fuller and Liu prescription, however, you get these closed circles at the bottom, and they're all zero spin So nothing is spinning, which is great for gravitational waves, but you might also ask yourself, okay, if I can never form a rapidly spinning black hole at the end, then how do I form GRBs, for example? So I think it's still a little bit unsolved, but this is a very interesting way to look at it. Okay, so even though we cannot confidently exclude all of these systems, all of these formation channels, there are some formation channels that we are more certain about that they are inconsistent with what the data tells us. And in particular, I want to again highlight the hierarchical channel. We've heard this argument kind of by the by now a few times, but hierarchical mergers are really cool because they make a super strong prediction for the spin. They basically tell you the system that came from a previous merger has a spin of about 0.7, and the mass ratio of the system will be about 0.5. And so given this information, you can see, or you can, and lastly, if they're dynamically assembled, you expect the orientation to be isotropically distributed. So if you take that, then you actually get a strong prediction for the mean chi-effective that you should get and the width of the chi-effective that you should get. And basically that prediction is this red mark. So we expect the mean chi-effective to be at about 0, and we expect the width to be quite broad, or the standard deviation. And that's just inconsistent with the data, which is this blue line. The data really prefers slow, narrow spins for systems that live in this 35 solar mass peak. And so I think this is really cool because we can kind of confidently say that the arguments that people have made of, oh, maybe you have the 9 solar mass peak, which double merges into the 20, which double merges into the 30, is not true. This is not consistent with the data. Okay, in the last few minutes, I'm not going to do this justice, but I want to talk very briefly about the subpopulations above the 30 solar mass peak. And specifically, I want to talk about this question of where is this parent stability supernova limit? So Aditya this morning already briefly introduced that we expect that very massive stars explode prematurely, leave no black holes behind, and we're pretty sure that this happens at some point. But that at some point is heavily dependent on us not really knowing the carbon-oxygen reaction rate, carbon alpha capture here. So this is first found by Rob Farmer, who made this beautiful plot showing that the upper and lower edges of this parent stability gap can range from like 45 to about 100 solar masses. People have done a lot of updates, in particular this work by E.B. Farag, but it still shows that you can push this gap down to about 45 solar masses and all the way up to 90 solar masses, but not much beyond. However, we see black holes with masses above these masses, so maybe they come from a hierarchical formation or from other formation channels. And so Fabio Antonini was the first to point this out in saying that we can use this spin argument again and not just look for a gap or changes in the mass function, but we can look for if there are changes in the spin distribution of this high mass subpopulation. And they indeed find that there's evidence for a much broader spin distribution, and for the same reasons that I explained just before, for systems above 45 solar masses, and there's this narrow peaked distribution for systems below 45 solar masses. Another paper by Yui Tong confirmed the same finding, but they went one step further, and they also inferred a gap for M2. They said the gap is not visible in M1, but it is in M2, and if you put a gap function in M2, you actually find that it lies at 45. So you might all say, yay, we found it. The gap is at 45. But then came Anaria Ray and Vicky Calogera, who said, whoa, 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 not so fast. As I mentioned before, you get what you order. And if you put in a gap in your M2 distribution, you're going to find a gap in your M2 distribution. that doesn't per se mean that there is a gap in your M2 distribution. And they argue that a slow decline is actually preferred over a gap. And they also question that the mass ratios of these high mass stars are not so strongly peaked at 0.5 as you would expect for hierarchical mergers. So I want to end my talk just very brief notes of caution in general, that you get what you order is more broadly applicable. We're living at a really, really fun time where we can use all these binary black hole observations to get different subpopulations. But if you put in a peak in your peak model, then you get a peak. And this is what, for example, Shumendra also is showing, and more people are showing now, that maybe the 35 solar mass feature that we've always described as a peak is not at peak at all. If you allow for a smooth transition rather than a peak to be there in M2, which is what you see on the right side here, there's no peak feature at the 35 solar masses. Okay, so I'm gonna, with that, just leave you with my very biased picture of what I think the subpopulations in the binary black hole general population are, and I will take questions.
Oh, okay. Let's see. I'll go to this part of the room first, because...
Thank you. Thank you very much, Lieke. One question, one comment. So the question is about your stable mass transfer channel, which is giving you a peak at 9 solar masses. So you explained why there is a very particular distribution of mass ratios that you're getting. That makes perfect sense to me. But why is stable mass transfer giving you a peak at a particular mass? And I understand that the overall scale has to come from something like, for example, mass loss in winds, but that should be metallicity dependent. And because gravitational wave detectors integrate over all metallicities, that should smooth out those kinds of peaks. So, yeah. So what is giving you a unique mass?
It's not actually wind dependent at all. It's the exclusion of systems below a certain mass. So as you can see in this figure here, the stable mass transfer channel in this form cannot form any black holes below about 8 solar masses, even though they're allowed to form by your remnant mass function. And so there's no added complication of metallicities or winds or whatever, because you just never form them. But also there's a flip side to this that says that all the black holes with lower masses, lower primary masses at least, than what is it, in this particular variation it's 5 solar masses, cannot come from the stable mass transfer channel, and they must have formed, for example, through the common envelope channel. And so this is why I think this mass peak, of course you can shift it up and down in the rates if you change your efficiency in the winds, etc. But I don't think this line, kind of this cutout, that really sets the boundary, and then above it, it is kind of a power law going down.
But it's not a power law, right? Because I mean, you do see. I mean, the reason you call it a peak is that actually there's a dip below that before another, relative rise, right? I mean, what you're seeing. Okay, sorry. Yes.
Yeah.
Exactly.
So this peak here is also caused by this second kind of cutoff, where the physics behind it here is that your mass ratio reversal will happen at some mass. Where that happens is set by your assumptions for your core mass size, your accretion efficiency, etc. But there's a second line, you should actually kind of see a second line going up here that does exactly the same as the line over here that prevents you from forming any mass ratio reverse systems with masses below something. And that's why you get a reduced number of systems from non-mass ratio reversed, and then you get this cutoff to the second mass. That makes sense.
I still don't understand I still don't understand what says the physical mass scale, but I'll have to ask you later then, because something has to set a physical. I understand what says a mass ratio scale. I don't understand what sets a physical mass scale. Why does it happen at 18 solar masses and not at 200 solar masses?
It's an exclusion rather than a inclusion kind of thing. Okay, we'll talk over that break.
So my So my question, well, I have multiple questions, but my main question was all related to these topics. So first of all, if you go to your previous, where Ilya was asking, so when you did this study, you were producing binary black holes through common envelope, but you ignored them,
Yes.
motivated by Monica Gallegos Garcia's work, who found through MESA simulations that the dominant channel is stable mass transfer. So first I want to ask, for the subsequent simulations and papers and predictions, are you still ignoring the common envelope channel and seeing the peak in the mass ratios and the peak in the other plots? So
Yeah,
that's one question.
That's a very fair point. Indeed, I am assuming that we do common envelopes wrong in population synthesis. And essentially, I expect that more systems would go stable if they were treated correctly, but also that many more systems would lead to a common envelope merger rather than successful ejection. And so I'm ignoring them, but also mostly my goal is to quantify the characteristics of this specific channel.
Sure. But the reason this is important is because it all depends on the fact that there is an assumption about Q-crit and an assumption about, in these models, about accretion efficiency. So now if you go forward to the Chen et al. Predictions, those are predictions, but for specific assumptions of these quantities.
Yes.
While in models with MESA, there is no assumption of Q-crit. It is what the stellar profiles are doing. Yes,
yes and no.
but it's not a fixed Q-crit,
Yeah, okay,
Selma.
but say, for example, F-core.
It's not even beta an assumption, it's a mechanism for that. So let me say the following. The mass ratio reversal is very accretion dependent.
Yes.
And yes, MESA has a very specific, strong, I know the papers, strong treatment that predicts low accretion efficiency. So all of these, even from MESA, I don't see them as predictions. I see them as, this is what the models are giving, so let's see where the Q distribution is peaking.
The same is the truth here. Like, one of the main points, even for Jackson's paper, is to show that you get this behavior if you take this model. But I would argue, again, even in MESA, and you know all this, but indeed the beta, for example, the accretion efficiency, is set by the assumptions that are in MESA that are on how you use rapid spin-up. But F-core as well, F-core, of course. Now I oversimplify everything here, but it's nothing more than the mixing boundaries, mixing bang theories, and how much you grow, etc. So these parameters might not be showing reality, but I think qualitatively, I expect these things to hold.
That all of us, we're not predicting necessarily where the peak is. We're guided from the light.
Okay, I think we can maybe take a bit of a different question now, and I will go to the back of the room.
Thank you for your talk. Can you please show the picture for mass distribution, different channels slide again?
That's what?
Yeah, I really like this slide. Just had a quick question. How can we distinguish the low mass scenario binary evolution from high metallicity dynamical formation scenarios?
It's a good question. I think it's hard, especially at the point that, I mean, in dynamical scenarios as well, you deal with binaries, right? You put binaries into your dynamical scenario. So it's always a double layer. Like, just as in binaries, we deal with single stars, but then in pairs. So there's always that uncertainty. But I would say that one of the things of dynamical formation is that you prefer to interact with the most massive things because, you know, they do more dynamics. And so this is why I think you actually get most of these systems really predict more systems at the higher masses, and I think I have a backup slide for those two systems with a primary mass of 15 solar masses, people were already asking, oh, does that actually, is that actually even possible with globular clusters? Okay, I have way too many backup slides. Oh no, it's here. Yeah. So, okay, so these are those two systems. I think even though it's possible to form it at solar metallicity, here still the 10 solar mass systems are not really formed in the dynamical scenario here. So broadly, I would expect dynamical formation to be more dominant at higher masses. And another distinguishing factor would be orientations of the spins, for example, or the hierarchical thing with the spin of 0.7.
Maya, I'm coming your way.
Thanks for the great talk. I definitely share your caution about highly modeled population inference. But I wanted to just clarify what Hui Tong's paper found, the first one you showed, with the hierarchical mergers at lower masses. That's actually that's a data-driven result. So the fraction of broad chi-effective there could be any kind of function. It could have many transitions. It's modeled as a Gaussian process. So the distinction of like M low, M mid, and M high is not made a priority. It just results from this fit.
Okay, we should have a more, well, maybe, I don't know if you have a question as well, but.
Oh, yes, sorry, my question is actually not about this. It's about when you were like ruling models in or out based on the redshift evolution, and I noticed like you had like thing for POP3 and chemically homogeneous evolution, but not the other one. I was wondering like why the other ones were not filled in, and if you could say more about that.
Well, very quickly about this, but we should have a broader discussion. I agree with you, but if I understood correctly, but please correct me if not, because you're obviously more in the know. There was a constraint of these all being smaller or bigger than each other. So there's an order that is enforced here. And so I think if you look at the spin and mass posteriors, then there's some stuff that has a clear spin prediction up here, and there's some stuff that has a clear spin prediction up here or down there. So I was wondering if by enforcing the order of these transitions being like this way, you kind of enforce there to be something in between there. But okay, we should talk about that more in detail. Then you asked about the redshift for the POP3. So, so it's a bit debatable, but because we find that the redshift evolution with the rate evolution with redshift is the same as the general population as for the 30 solar mass population, we take that as an indicator that it's not from POP3 stars, but because we expect those to come from only the very highest redshift. So it would be a little bit fine-tuning of saying they came from the exact highest redshift and now they all merge today at redshift 0, and then they have a redshift evolution going back that looks exactly like the rest of the population.
Okay, last question.
Okay, so I have a question that's not about mass ratios. For the chemically homogeneous evolution channel, you were suggesting that the angular momentum transport law that you need to make that work causes problems for gamma ray bursts. But gamma ray bursts are all from whenever they found the supernova as a broadline type 1c supernova. So I would presume that that has a very different history because its envelope has been very heavily stripped. Does the physics still work out that you would really say that you can't get those stars to be spinning fast just because you can't get these ones to?
So I say this more based on a paper by Or Gottlieb, where Richard is also second author, so he might have more interesting things to say. But they basically we're using the same MESA models as they are, and they found that if you take these different models as well, you don't have enough spin to create a disk anymore. And so no disk is no GRB. So that's kind of what I was going for. I haven't actually linked it to observations.
Okay.
Okay, let's thank Lieke again.